that a particle of mass m is located in a unidimensional potential field where the potential energy of a particle depends on its coordinate x. So potential energy depends upon coordinate according to the equation potential energy as a function of x is equal to u naught into 1 minus cos ax, where u naught and a are constants. Find the period of small oscillations that the particle perform about the equilibrium position. So over here, just remember one thing is that the x over given over here is not the displacement from mean position. X is representing its coordinate. So first we can find out what about the value of force acting on it as a function of its coordinate x. So we know that F is equal to minus of du divided by dx, or if you're differentiating potential energy with respect to x, we'll get the value of force acting on it. So F is equal to nothing but minus of, if you're differentiating this equation, it is u naught into differentiation of 1 is 0, and minus cos ax differentiation will be equal to sine ax into differentiation of ax, that is a. So you can write the equation for F is equal to minus of u naught into a into sine ax. Now from this equation we can find out the value of equilibrium position. You can write when equilibrium position force will be equal to 0. So according to this equation, when F is equal to 0, the value of this ax should be equal to 0. Now we can find out if from this equilibrium position, if the particle is displaced by a very small distance, let's say dx, then we can find out what about the value of restoring force acting on it, represented by integral as df. So for that purpose, once again we can differentiate this equation. So if we can write as df will be equal to minus of u naught into a into sine, the differentiation of sine ax is nothing but a into cos ax. So you can write the equation for df into dx, to df as a function of x. So you can write the value of this df will be equal to u naught into minus of u naught into a square, and we are finding out the value of this restoring force when the particle is displaced by a distance x dx from its mean position, and the condition for mean position is the value of ax should be equal to 0. So over here, if you are putting the value of ax is equal to 0, the value of this cos ax becomes equal to this value becomes equal to 1. So you can write the equation for it is, that is df is equal to minus of u omegas u a square into, at equilibrium position, cos ax is 1 into dx. So we are basically getting this restoring force as a function of dx. So we can equate to the general equation, force equal to minus of m omega square into dx. So from this we can calculate the value while comparing these two equations. We can write the equation for omega, that is u naught a square divided by m under root will be the value of omega. So we can find out the equation for its time period, that is time period is 2 pi by omega. According to the situation, it becomes 2 pi into under root of m divided by u naught a square.